Hello and welcome to the second video of section 1.6 on limit laws. In this video, we will combine limit laws with a few small theorems to obtain 4 common limit calculation techniques. Limit laws were introduced in the previous section 1.6 video, and if you need to review that before viewing this video, please do. It is not 100% correct to refer to all of these as techniques. However, the order in which these are listed is very important. Direct substitution is a theorem used so often you usually won't be aware that you're using it. Simplification and conjugation are previously acquired skills that you should hone and be conscious of, and the squeeze theorem is very rarely used, but it can surprise you in its applications. With the direct substitution theorem, we are able to calculate the limit of two of the most familiar functions to many students, polynomials and rational functions. If an actual value exists, then the limit and the actual value coincide. Remember, a polynomial is made up of x powers and constants, summed and multiplied together. The domain of a polynomial is all real numbers. Therefore, a polynomial has a limit at all points, and this limit coincides with the actual value of the polynomial. A rational function is a function written as a polynomial divided by a polynomial. The domain of a rational function is any real number for which the denominator is non-zero. Let's take an example. We could use our limit laws to calculate the limit, but since this function is rational and x minus 2 is non-zero when x equals 3, we can use direct substitution, plug the value 3 into x, and obtain 15 for the limit as x approaches 3. But what if we were to look for the limit as x approaches 2? This is where simplification comes into play. We cannot calculate this limit using the direct substitution theorem, as the function is undefined at x equals 2. So how can we calculate this limit? First, notice that this function is not simplified. We can factor the numerator by first pulling out an x and then factoring a difference of squares, and then canceling x minus 2. We can write the rational function as a polynomial x times x plus 2. But this is not a correct expression, as the right-hand side is defined at x equals 2. In fact, when x equals 2, it is 8, while the left-hand side is undefined at x equals 2. To correct this error, it is important to write that x can't be 2 in order for this equality to hold. The natural question to ask is, what is the connection between the limit of our rational function and the limit of the polynomial it equals everywhere but x equals 2? It turns out that they are equal. Notice that the rational function and polynomial are equal everywhere but 2, therefore their limits as x approaches 2 are equal. With our ant visualization from section 1.5, it is easy to see why this theorem is true. We take the graph of f and g, with f colored blue, g colored red, and points in common colored purple. Notice that the points near A are all purple. The left-handed limit as x approaches A, the location Lefty the ant crawls towards, will be the same for both f and g, as both are represented by the same purple line. And the right-hand limit as x approaches A, the location Righto the ant crawls towards, will also be the same for both f and g. Therefore, the limit of g and f will be equal if they exist. You probably were first exposed to our third technique, conjugation, when you learned how to rationalize the denominator. A conjugate of the expression x plus y is x minus y. They are the twins in the factorization of the difference of squares, x squared minus y squared. Conjugation will prove useful in circumstances where having all elements be squared is useful. In particular, for finding the derivative of a square root, conjugates are necessary. Say we are trying to find the derivative of the square root of x at a equals 7. We'll use the alternative limit definition of the derivative. And plugging in 7 plus h into f and 7 into f, we end up with a limit where direct substitution won't work, as 0 is not in the domain, and we have a function which is simplified. We'll attack this limit by multiplying by the conjugate of the numerator. What is the conjugate of the numerator? We find the conjugate by flipping the middle sign, and we multiply by the conjugate divided by the conjugate, or 1. We use the conjugate property in the numerator. Remember that the conjugates form a twin to the factorization of the difference of squares. And we leave the denominator undisturbed. Because the square and the square root cancel each other out, we are left with 7 plus h minus 7. Cleaning up the numerator with arithmetic, we're left with h in the numerator and h in the denominator, which we cancel. Now notice that the limit of the denominator is non-zero. This means that we're in a position to use our limit laws. We use the quotient rule, moving the limit into the numerator and the denominator. And using direct substitution with h equals 0 in the denominator, we find that the derivative of the square root of x at 7 is 1 over 2 times the square root of 7. It might have slipped by you, but we made use of simplification between the yellow step and the green step. The yellow function is not defined at h equals 0 because of h in the denominator, while the green function is defined at h equals 0. The reason why the limits are equal is the simplification theorem from a few minutes ago. Our final technique is known by many names. We will call it the squeeze theorem, but it is also called the sandwich theorem or the pinch theorem. The squeeze theorem is a consequence of the observation that if one function g, colored in red, is larger than the function f, colored in black, then the limit of g is larger than the limit of f as x approaches a, provided the limit exists, of course. The squeeze theorem takes this observation and doubles it up with a squeeze in the middle. That is, there are three functions h on top of g on top of f near a, and the limit of f and h are equal as x approaches a. This pinches the limit of the middle function g to the same limit as h and f as x approaches a. Looking at this graph, you'd understand how the squeeze theorem sometimes is described as two friends helping a drunk through a door. The squeeze theorem works best with functions which are easily bounded, such as sine and cosine. It will also make a special appearance in section 2.4. This graph actually depicts the squeeze theorem on x squared sine 1 over x as x approaches 0. As sine is a function naturally bounded by 1 and negative 1, we can take the natural bound of sine by 1 and negative 1 and multiply it by x squared. What we have is three functions: x squared on top of x squared sine 1 over x on top of negative x squared. As x squared and negative x squared go to 0 as x approaches 0, the middle function is squeezed towards 0. Consider your toolbox for limit calculations to include these four techniques along with the limit laws. Be sure to strengthen your understanding through practice.